Okay, what you're looking at here is ozone depletion. This is again a computer-generated image of part of the southern hemisphere in 2007 that shows the ozone thinning over the Antarctic region. This thinning moves with air currents. And on the right, you see the average yearly ozone column over New Zealand from 1980 to 2006. This is located in the southern hemisphere, and New Zealand is vulnerable to increasing UV radiation due to this thinning. And we pointed out the fact that part of this is due to the use of CFCs in man-made components such as aerosols, but the sun also has a hand in this due to the proton content of the solar wind. Occasionally, when the solar wind reacts with the upper atmosphere, what it can do is actually deplete the amount of ozone in the stratosphere, and as a result cause this layer to thin and increase the amount of UV rays that actually hit the surface of the Earth. Other causes include CFCs such as Freon, which is a refrigerant. We see this in coolants and in aerosol propellants, and also in the manufacture of styrofoam. Halons, which are fire retardants. Methyl bromide, which is a pesticide, and methyl chloroform, which is an industrial solvent, as well as carbon tetrachloride, which is also an industrial solvent, and nitrous oxides, which come from the burning of coal and the breakdown of fertilizer. So what are some of the effects? Well, more UV reaches the Earth's surface, and as a result, this can change the ecosystem. For example, it can have a negative effect on areas such as the Antarctic, where the phytoplankton population is receiving the brunt of that impact. And it can cause damage to wildlife, such as Antarctic fish and amphibians. It also brings with it human health problems, such as an increase in cataracts and skin cancer, and it can tend to deplete the immune system. But again, we should point out that as with every change in an abiotic component of the environment, we can have a change in a biotic component as well. And the result of this are the selection for species that are UV resistant. An example would be species that tend to have more melanin in the skin as a shield against the damaging UV rays of the sun. And we see an increase of that in regions that experience more UV. This is why, for instance, in regions of the world where we have a lot of sun exposure, such as in Africa and South America, we tend to see more darkly pigmented human beings living in those regions. This is, again, an adaptation to the increased rays of the sun in order to enhance survivability. Just one example. So how can we deal with this particular problem? Well, there's two approaches. There's mitigation and there's recovery. We've had worldwide bans and reductions in the use of CFCs. In '78, the U.S. banned CFC use as a propellant. In '87, the Montreal Protocol called for a 50% reduction by '98. CFCs were phased out by '96 in developed countries and by '05 in developing countries. CFCs are extremely stable, and they continue to deplete stratospheric ozone decades after decades. Full recovery is expected sometime after 2050. So we get to our next block of concept checks. First question is, what is the stratospheric ozone layer? And what it is an ozone layer that encircles the planet 10 to 45 kilometers above the Earth's surface. That's between 6 and 28 miles. Next question, what does the ozone layer protect in terms of life on Earth? And what it does is it shields us from the UV radiation that comes from the sun, which is a carcinogen and a mutagen. It absorbs about 99% of the incoming solar UV radiation. If the ozone disappeared from the stratosphere, the Earth would become uninhabitable for many forms of life. Next question, what is stratospheric ozone thinning? Well, this is the removal of ozone from the stratosphere by human-produced chemicals or natural processes. Next, what role do CFCs play in this thinning? Well, they are the primary chemicals responsible for ozone loss in the stratosphere. But again, we have to acknowledge that there is also an effect from the solar wind. Next question, What are two harmful effects of ozone depletion? Well, these include problems such as skin cancer and weakened immunity due to increased levels of UV radiation reaching the Earth's surface. But we should also point out that in its role as a mutagen, UV radiation also is a driver of evolution. So with every negative effect, there's also a potential positive effect on the back end. Okay, next thing we want to look at is acid deposition. We're going to define acid deposition and explain how it develops, and we'll relate examples of the effects of acid deposition. So it's a type of air pollution. Sulfuric and nitric acids in precipitation are the result of primary pollutants reacting with water and forming these powerful corrosives. The dry acid particles settle out of the air. It's been observed since the Industrial Revolution, and it's a serious threat to the environment. In the U.S. alone, annual damage is estimated at 10 billion, and in China, acid deposition affects about 40% of the country. So how does it develop? Well, sulfur and nitrogen effluents are released by fossil fuel burning. The wind then carries the pollutants throughout the atmosphere that reacts with the water. This forms acids such as nitric and sulfuric acid, which are precipitated in rain, sleet, fog, or snow as dry particles. And here you can see how the cycle operates. Here you can see the acid rain cycle. Again, sulfur dioxide and nitrogen oxide emissions react with water in the atmosphere, and this forms acids that return to the surface as dry or wet deposits. And of course, this has an impact on the ecosystems that experience this phenomena. But we should also point out again that with every abiotic change, there is a biotic change, and longitudinal studies have been done in areas of the country, particularly in North America, that have been downwind of what we traditionally call the Rust Belt. And what we've seen over time is the prevalence of acid-resistant species in these wooded areas as a response to this change in selection pressure in the ecosystem produced by this particular phenomenon. So again, life fills a vacuum. What are some of the effects? Well, we see a decline in fish and bird populations. We see a decline in forest ecosystems, damage to the agriculture, damage to metals, building materials, and statues, changes in soil chemistry, and we also see, along with this, the leaching of nutrients from the soil and a decrease in the soil's pH. So what this does is paves the way for organisms that are acid resistant to now move into this ecosystem. Here you can see an example of some of these effects. This is acid rain damage. The rain has destroyed much of the detail from this stone sculpture. This was taken in London. Again, the corrosive effects have worn it away over time. Here's an acidic stream. This Adirondack stream is acidic because of years of acid precipitation that have altered the soil chemistry. And with that, what we see now are organisms that are acid tolerant. Okay, so again, the ecosystem changes, the abiotic components change, and the living components change as well. So how do we deal with this phenomenon? Well, this falls in the political realm, among many others. Sulfur and nitrous oxides produced in one place are transported and deposited hundreds of kilometers away. The Midwest produces about 75% of the acid deposition that pollutes New England and Canada. Coal-burning pollution from England is blown away to Sweden and Norway, and so the question becomes, who pays for this damage? And of course, it's a matter of much debate. So how do we facilitate recovery from this phenomenon? Well, we can reduce emissions of sulfur and nitrous oxide and reduce their deposition. We can install scrubbers and smokestacks of coal-fired plants and use clean coal technology when burning it. And we can switch from high sulfur to low sulfur coal and reduce the use of gasoline and diesel engines. We've also pointed out in class that mobile carbon scrubbers and pollutant technology is being developed for the use in vehicles that utilize an internal combustion engine. And as a result, we can expect to reduce the carbon footprint and the amount of pollutants that are produced as a result of exhaust coming from these vehicles. So again, the third way, I think, is the most productive and people are engaging in it because we have to both reduce our footprint on the ecosystem while maintaining our standard of living and allowing the economy to expand. So we get to our last set of concept checks for this chapter. What is acid deposition? Well, it's a type of air pollution that includes sulfuric and nitric acid in precipitation, as well as dry acid particles that settle out of the air. Next question, what is the main source of this atmospheric acid? And these include motor vehicles, coal-burning power plants, large smelters, and industrial boilers. Next question, what are the harmful effects of acid deposition on materials, aquatic organisms, and soils? Well, it corrodes metals, buildings, and other materials, as well as statues. It's caused fish populations to decline and has adversely affected egg production in birds. It also causes soils to become acidic and interferes with their ability to absorb calcium, which is an important component in the physiology of most organisms. Next question. Why does managing acid deposition often require international cooperation? This is because emissions from one country can contribute to acid deposition in another country. Okay, that brings us to the end of Chapter 9. Make sure and review this material in preparation for the test next week, and I'll see everybody in class.